For decades, we believed salvation waited just beyond our solar system. Proxima Centauri b. TRAPPIST-1. Planets orbiting in habitable zones, promising oceans, atmospheres, maybe even life. We built our hope on models that painted nearby star systems as Earth's potential neighbors. James Webb Space Telescope just shattered that illusion. The data streaming back from our most powerful eye in the sky reveals something disturbing. The closest promising worlds are not what we imagined. They are being stripped, irradiated, chemically poisoned by their own stars. Atmospheres we assumed existed are vanishing. Surfaces we thought might harbor water are scorched wastelands. Our nearest cosmic neighbors are far more hostile than any model predicted. The local habitability illusion is collapsing. If you enjoy exploring our cosmic neighborhood, tap that like button and subscribe. Now, settle in, get yourself comfortable. Let's begin. The night sky tells a comforting lie. Those twinkling points of light seem close enough to reach, intimate enough to harbor neighbors, promising enough to hold our cosmic future. For 3 decades, astronomers reinforced this illusion with discovery after discovery: planets orbiting nearby stars, worlds sitting in habitable zones, candidates for liquid water, stable atmospheres, perhaps even life. The message seemed clear. Earth is not alone in having the conditions for biology. Our stellar neighborhood teems with possibility. James Webb Space Telescope is rewriting that story in data we cannot ignore. The first exoplanet orbiting a sun-like star was discovered in 1995. A gas giant hugging its parent star so closely that its year lasted just over 4 days. This world offered no hope for habitability, but it opened a floodgate. Within 2 decades, astronomers confirmed thousands of planets orbiting other stars. Statistical models suggested that virtually every star in our galaxy hosts at least one planet. The Milky Way alone might contain more planets than stars, but quantity was never the real question. The search always centered on one specific type of world: rocky planets orbiting within their star's habitable zone, the region where temperatures allow liquid water to exist on a planetary surface. Too close to the star, and water boils away. Too far, and it freezes solid. This Goldilocks zone represented the sweet spot for life as we understand it. The nearest star system to Earth became the first great hope. Proxima Centauri sits just 4.2 light-years away. In astronomical terms, this makes it a next-door neighbor. A single light-year spans roughly 6 trillion miles. Proxima Centauri lies approximately 25 trillion miles from our Sun. Light leaving that star tonight will reach Earth in just over 4 years. Radio signals travel at the same speed. A message sent to Proxima Centauri could receive a reply within a human lifetime. Think about what that proximity represents. If the entire Milky Way galaxy were compressed to the size of the United States, the distance between our Sun and Proxima Centauri would span roughly 6 inches. 2 stars sitting practically on top of each other in cosmic terms. 2 stellar furnaces burning close enough that light can make the journey while a human child grows into adulthood. In 2016, astronomers announced they had found a planet orbiting Proxima Centauri within its habitable zone. Proxima Centauri b appeared to be a rocky world slightly larger than Earth. Its orbital period measured just 11 days, but because its star burns so much cooler than our Sun, this tight orbit placed the planet squarely in the temperature range where liquid water could theoretically exist. The discovery sparked genuine excitement across the scientific community. Here was a potentially habitable world orbiting the closest star to our solar system. If humanity ever developed interstellar travel capability, this would be the obvious first destination. Breakthrough Starshot proposed sending tiny spacecraft propelled by powerful lasers toward Proxima Centauri. The probes would reach roughly 20% of light speed, arriving at the system within 2 decades of launch. Media coverage exploded with possibilities. Artists rendered oceans, reflecting alien sunsets. Writers imagined civilizations developing on temperate shores. Scientists spoke carefully about the conditions that might exist on this neighboring world. The public heard what it wanted to hear. Earth has a cousin next door. The optimism surrounding nearby habitable worlds did not emerge overnight. It built systematically across 2 decades of increasingly exciting discoveries. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science by staring continuously at a single patch of sky containing roughly 150,000 stars. Over 9 years of operation, Kepler discovered more than 2,700 confirmed exoplanets. The mission revealed that planets are not rare exceptions but common outcomes of star formation. Statistical analysis of Kepler data suggested that rocky planets in habitable zones might number in the billions across our galaxy alone. These statistics fueled enormous optimism. If billions of potentially habitable worlds existed, surely some must orbit nearby stars. The galaxy seemed to overflow with real estate suitable for life. Researchers began speaking not of whether habitable exoplanets existed, but of when we would confirm their atmospheres and search for biosignatures. The K2 mission extended Kepler's work after reaction wheel failures limited the original telescope's pointing capability. K2 surveyed different regions of the sky, discovering additional planets around nearby stars that Kepler's original field had not covered. Each discovery added to the growing catalogue of worlds that might harbour conditions suitable for biology. Ground-based surveys contributed their own discoveries. The HARP spectrograph in Chile detected planets through the radial velocity method, measuring tiny wobbles in stellar motion caused by orbiting planets. HARPS found rocky worlds around some of the nearest red dwarf stars, including the planets orbiting Proxima Centauri that sparked such excitement in 2016. The cumulative effect of these discoveries created a narrative of cosmic abundance. Popular science articles proclaimed that Earth-like worlds were common. Documentary films imagined oceans and continents on planets orbiting nearby stars. The public absorbed a message that habitable real estate waited just beyond our solar system, accessible to future generations who developed the technology to reach it. This narrative contained an assumption that Webb is now testing directly. The assumption held that planets in habitable zones would generally possess the atmospheric and chemical conditions necessary for life. Temperature alone seemed sufficient to define habitability. If a planet orbited at the right distance for liquid water, water would exist. The assumption seemed reasonable, given our limited information. We could measure planetary masses and orbital periods. We could calculate equilibrium temperatures. We could not measure atmospheric composition or surface conditions. The gap between what we could observe and what habitability required was filled with optimism that Webb's observations are now systematically dismantling. The space agencies planning Webb's mission understood that atmospheric characterization would be among its most important capabilities. The telescope was designed specifically to analyze exoplanet atmospheres through transit spectroscopy. Its infrared instruments would detect molecular signatures that previous telescopes could not resolve. Webb would transform habitability from theoretical possibility into observational fact. What no one fully anticipated was how thoroughly Webb's observations would contradict the optimistic assumptions embedded in habitability estimates. The telescope is performing exactly as designed. Its instruments achieve the sensitivity specifications engineers promised. The problem is that the universe does not match the models we built during the decades when direct observation remained impossible, but the excitement rested on assumptions. Models predicted what Proxima Centauri b might look like based on limited data. We knew its minimum mass. We knew its orbital period. We knew its distance from its star. Everything else was extrapolation. The planet's atmosphere, if it had one, remained completely unknown. Its surface conditions were pure speculation. Scientists assumed that a rocky planet in a habitable zone would have retained an atmosphere over billions of years. They assumed that liquid water could exist under those conditions. They assumed the star would be friendly enough to allow complex chemistry to develop. Those assumptions built a foundation of hope that is now cracking under the weight of direct observation. James Webb Space Telescope possesses the capability to test these assumptions directly. Its infrared instruments can analyze light passing through or reflecting from exoplanet atmospheres. Different molecules absorb different wavelengths of infrared radiation. By measuring which wavelengths are missing from starlight filtered through a planetary atmosphere, Webb can determine what chemicals that atmosphere contains. This technique, called transit spectroscopy, works when a planet passes between its star and Earth. During transit, a tiny fraction of starlight filters through the planet's atmospheric envelope. That filtered light carries the chemical fingerprints of whatever gases surround the planet. Methane, oxygen, nitrogen, each molecule absorbs its own specific wavelengths. Webb's instruments achieve sensitivity levels that previous telescopes could not approach. The James Webb Space Telescope operates in infrared wavelengths, detecting heat signatures and molecular absorption features invisible to optical instruments. Its mirror spans 6.5 meters across, collecting vastly more light than the Hubble Space Telescope. Its position at the second Lagrange point, roughly 1 million miles from Earth, shields it from our planet's infrared glow. This technological leap promised answers to questions astronomers had debated for decades. Do nearby rocky planets possess atmospheres? What chemicals do those atmospheres contain? Could any of these worlds support liquid water on their surfaces? The results are not what anyone hoped. Consider the TRAPPIST-1 system. This collection of 7 Earth-sized planets orbiting an ultracool red dwarf star sits roughly 40 light-years from Earth. 3 of these worlds orbit within the star's habitable zone. When the system was announced in 2017, it became the poster child for nearby habitable real estate. 7 rocky worlds packed into tight orbits around a small, cool star, at least 3 candidates for liquid water and atmospheric chemistry. The TRAPPIST-1 discovery represented everything the exoplanet community had been searching for: a compact system where multiple worlds might harbour conditions suitable for life. The planets orbit so closely together that standing on one world, you could see neighbouring planets as clearly as we see the Moon from Earth. Some of those planets might show continents and oceans to observers on their neighbours. The system's star burns at roughly 2400 degrees Celsius, compared to our Sun's 5500 degrees. This cooler temperature means the habitable zone sits much closer to the star. TRAPPIST-1's 7 worlds all orbit within the distance that Mercury maintains from our Sun. Their years last between 1.5 days and nearly 19 days, tight orbits around a dim, cool star. Webb turned its instruments toward TRAPPIST-1b, the innermost planet of the system, and found something troubling. Thermal emission measurements revealed a surface temperature consistent with a world lacking any substantial atmosphere. The planet appears to be bare rock exposed directly to the harsh radiation environment of its star. No protective layer of gases softens the stellar assault. No greenhouse effect moderates temperature extremes. The measurements showed the planet's dayside temperature matching predictions for an airless body. Roughly 230 degrees Celsius. Hot enough to melt lead on the sunlit face. Cold enough to freeze carbon dioxide on the dark side. No atmosphere to redistribute heat between day and night. No buffer against the star's radiation. Just rock baking under eternal starlight. This result challenges decades of modelling assumptions. Theoretical predictions suggested that rocky planets orbiting red dwarf stars could retain atmospheres if they possessed sufficient magnetic field strength and initial volatile content. TRAPPIST-1b orbits close to its star, true. But models indicated that atmospheric retention should still be possible under certain conditions. The data says otherwise, but TRAPPIST-1b was always considered marginal. It orbits too close to its star to fall within the traditional habitable zone. The real hope rested on the outer planets. TRAPPIST-1d, E, F and G sit within or near the temperature range where liquid water could theoretically exist. Surely these more temperate worlds would show evidence of atmospheric preservation. Webb observations of TRAPPIST-1c delivered another blow. This world, slightly larger than Earth and positioned at the inner edge of the habitable zone, also shows minimal evidence of atmospheric retention. The thermal signature suggests a rocky surface without significant atmospheric pressure. Another bare world, exposed to stellar radiation. The observations revealed a dayside brightness temperature of roughly 380 Kelvin. No significant atmospheric absorption features appeared in the data. No evidence of the greenhouse warming that would indicate trapped gases redistributing heat. This brings us back to the real problem. The local habitability illusion is collapsing under the weight of direct observation. For years, we built models based on what we thought should be true. Rocky planets in habitable zones should retain atmospheres. Liquid water should be possible under the right conditions. Life should have opportunities to emerge on worlds orbiting nearby stars. Webb is showing us what actually exists, and the picture is far grimmer than our models suggested. The gap between prediction and observation grows wider with each new data release. Atmospheric modeling relied on assumptions about planetary magnetic fields, volcanic outgassing rates, stellar wind intensities, and dozens of other variables we could not measure directly. Those assumptions were reasonable extrapolations from solar system experience and physical theory. Consider what we assumed about planetary atmospheres around red dwarf stars. These small, cool stars were thought to be ideal hosts for habitable planets in some respects. Their longevity exceeds that of sun-like stars by factors of hundreds. A red dwarf can burn steadily for trillions of years, providing billions of times more opportunity for life to develop than our Sun's 10 billion-year lifespan. Habitable zone planets around red dwarfs orbit close enough for tidal locking, yes, but models suggested that atmospheric circulation could distribute heat effectively even on worlds with permanent day and night sides. The theoretical advantages seemed compelling. A civilization arising on a planet orbiting a red dwarf would have cosmic time to develop. Our Sun will exhaust its hydrogen fuel in roughly 5 billion years. A red dwarf of similar mass to TRAPPIST-1's star could burn for 10 trillion years. That represents 1,000 times more opportunity for life to emerge, evolve, develop intelligence, and spread across space. What the models underestimated was the violence of these stars during their youth and throughout their extended lives. Red dwarf stars do not burn quietly. They flare unpredictably. They emit bursts of X-rays and ultraviolet radiation that dwarf anything our Sun produces. They strip atmospheres from their closest companions through processes that operate continuously over billions of years. The physics of red dwarf activity creates a paradox at the heart of habitability calculations. These stars live longest, but they also rage hardest. Their magnetic fields generate flares that can briefly double the star's brightness. Their coronae produce X-ray emissions hundreds of times more intense than our Sun's output. Their stellar winds blast outward with particle densities that would erode Earth's atmosphere within millions of years. Webb is not the only instrument revealing this hostile reality, but it provides the most direct evidence yet that our nearest candidate worlds have already lost whatever atmospheric protection they once possessed. The telescope's spectroscopic capabilities allow detection of atmospheric signatures at levels previous instruments could not achieve. When Webb points toward a nearby system and finds no atmosphere, that result carries weight that earlier non-detections could not claim. Previous observations left room for doubt. Perhaps the instruments lacked sensitivity. Perhaps the atmospheric signatures existed below detection thresholds. Perhaps we were measuring at the wrong wavelengths. Webb eliminates those escape routes. Its sensitivity exceeds previous instruments by orders of magnitude. Its wavelength coverage spans the infrared regions where atmospheric molecules show their strongest absorption features. When Webb finds nothing, the nothing is real. The implications extend beyond individual planetary systems. If the closest star systems to Earth contain worlds that cannot retain atmospheres, what does this suggest about the broader distribution of habitable real estate in our cosmic neighborhood? Red dwarf stars dominate our stellar surroundings. Roughly 3/4 of all stars within 100 light-years of Earth are M-class red dwarfs. These small, cool stars outnumber Sun-like G-class stars by enormous margins. For every sun in our cosmic neighborhood, there are roughly a dozen red dwarfs. The galaxy produces small stars far more efficiently than large ones. This stellar census seemed like good news for decades. More stars meant more planets. More planets meant more chances for habitable conditions. The sheer abundance of red dwarfs suggested that habitable worlds should be common, even if they were rare around any individual star. If red dwarf systems prove universally hostile to atmospheric retention on close-orbiting planets, then the majority of nearby star systems offer no habitable prospects whatsoever. 3/4 of our stellar neighbours become cosmic dead ends. Destinations not worth reaching. Systems where no amount of technological development could create conditions suitable for Earth-based life. This concentration of hostile environments close to Earth was not part of the optimistic narrative that developed over the past 30 years. The discovery of exoplanets led to statistical estimates suggesting billions of potentially habitable worlds in our galaxy. Those estimates may still be accurate at cosmic scales, but they obscure a more troubling local reality. The galaxy may indeed contain billions of habitable planets, but they may be far more distant than we hoped. Consider what the numbers actually mean. Astronomers estimate that the Milky Way contains between 100 billion and 400 billion stars. If even 1% of those stars host habitable planets, the galaxy contains billions of such worlds. The statistical argument for abundant life seems overwhelming, but statistics can mislead when distributions are uneven. Imagine a nation with an average income of $100,000 per year. That average might hide a reality where most citizens earn $20,000 while a small minority earns millions. The average tells you nothing about what most people actually experience. Habitable planets may follow a similar distribution. They might exist in enormous numbers across the galaxy, while being vanishingly rare in our immediate vicinity. The red dwarf problem creates exactly this kind of uneven distribution. Our local neighborhood swarms with small stars that strip atmospheres from their planets. Habitable worlds cluster around sun-like stars that make up only a small fraction of the stellar population. Webb's observations are forcing a fundamental recalculation of where we might find genuinely Earth-like conditions. The nearest habitable world may not orbit the closest stars. It may lie dozens or hundreds of light-years away. Beyond the reach of any interstellar mission humanity could reasonably contemplate with current or near-future technology. This realization carries profound implications for humanity's cosmic future. The dream of interstellar settlement assumed that nearby star systems would offer destinations worth reaching. The energy requirements for interstellar travel are staggering, regardless of destination, but a journey to a star 4 light-years away is qualitatively different from a journey to a star 100 light-years distant. 4 light-years could theoretically be crossed within a human lifetime using advanced propulsion systems that remain within known physics. Laser sail technology, nuclear pulse propulsion, antimatter engines, these concepts face enormous engineering challenges, but they do not violate fundamental physical laws. A probe traveling at 20% of light speed would reach Proxima Centauri in approximately 20 years. The Breakthrough Starshot initiative proposed exactly this approach. Tiny spacecraft weighing just a few grams would be accelerated by powerful ground-based lasers. The probes would reach Proxima Centauri within a single human generation. Data would return to Earth within another 4 years. Scientists who launched the mission could live to analyze its results. 100 light-years requires either vastly longer mission durations or propulsion systems that approach speeds we cannot currently achieve. Even at 10% of light speed, a journey of 100 light-years requires a millennium. Generation ships carrying human populations across such distances would need to function as self-sustaining ecosystems for dozens of generations. The engineering challenges multiply with distance. Life support systems must function for centuries without external resupply. Social structures must maintain mission focus across 40 generations of crew members. Genetic diversity must be preserved in isolated populations. Energy systems must operate reliably far longer than any human technology has ever functioned. The local habitability illusion collapse is not just an abstract scientific discovery, but we must be careful not to overstate conclusions from early Webb observations. The telescope has examined only a handful of nearby exoplanets in atmospheric detail. Many more targets await investigation. Some may prove more promising than the initial results suggest. The outer TRAPPIST-1 planets remain under study. TRAPPIST-1e, sometimes called the most Earth-like exoplanet yet discovered, orbits in the middle of its star's habitable zone. Its mass and radius suggest a rocky composition similar to Earth's. Models predict that it receives roughly the same amount of stellar energy that Earth receives from our Sun. If any planet in the system retains an atmosphere, this would be the most likely candidate. Webb observations of TRAPPIST-1e continue. The data requires careful analysis to distinguish genuine atmospheric signatures from instrumental artifacts. The planet transits its star less frequently than the inner worlds, limiting observation opportunities. Scientists expect results within the next observing cycles, yet the pattern emerging from early data is consistent and troubling. World after world in nearby systems shows evidence of atmospheric stripping, surface exposure, and conditions incompatible with liquid water or Earth-like chemistry. These are not random outliers. They represent the expected outcome when rocky planets orbit too close to active red dwarf stars. The physics behind atmospheric erosion operates continuously. Stellar winds carry charged particles outward from the star. These particles interact with planetary atmospheres, gradually stripping away lighter elements like hydrogen and helium. Ultraviolet radiation breaks apart water molecules, allowing hydrogen to escape into space. X-ray flares deliver massive energy pulses that can drive atmospheric loss events visible across interstellar distances. Earth loses roughly 3 kilograms of hydrogen to space every second. This loss rate remains sustainable because our magnetic field deflects most solar wind particles and our distance from the Sun limits radiation exposure. A planet in TRAPPIST-1's habitable zone would face vastly higher loss rates. The stellar wind intensity at that distance exceeds what Earth experiences by factors of hundreds. The ultraviolet exposure could be thousands of times higher during flare events. Models predicted these effects but underestimated their cumulative impact. A planet might lose its entire atmosphere over geological timescales if the stripping rate exceeds the replenishment rate from volcanic outgassing or cometary delivery. The TRAPPIST-1 observations suggest that at least the inner planets of that system crossed this threshold long ago. Volcanic activity can replenish atmospheric gases lost to space. Earth's volcanoes continuously release carbon dioxide, water vapor, and other volatiles that maintain our atmospheric inventory. Mars once possessed volcanic activity that sustained a thicker atmosphere. When that activity ceased, atmospheric loss to space eventually stripped the red planet down to its current tenuous envelope. The balance between loss and replenishment determines whether a planet retains its atmosphere over cosmic time. Even worlds with active volcanism might not produce enough gas to replace what stellar activity strips away. This brings us back to the real problem that Webb's observations are revealing. Our nearest cosmic neighborhoods are not friendly territories waiting for human exploration. They are harsh environments where the conditions necessary for life struggle to persist. The hope that once attached to nearby star systems must now migrate outward. Somewhere beyond the hostile red dwarf zone, sun-like stars may host planets that retain their atmospheres, worlds where liquid water flows on stable surfaces, environments where the chemistry of life could develop undisturbed. Sun-like stars present different challenges. They are far less common than red dwarfs. Their habitable zones sit at greater distances, making transit observations more difficult. Planets in these temperate regions orbit with periods measured in years rather than days, limiting how often Webb can observe them. The search for habitable worlds around sun-like stars will take longer and yield fewer candidates. But those worlds, if they exist, lie far beyond easy reach. The nearest sun-like star with a confirmed planet in its habitable zone may orbit dozens of light-years from Earth. That distance transforms interstellar travel from an ambitious engineering project into a civilizational commitment spanning centuries. The local habitability illusion has collapsed. What remains is a cosmos that guards its treasures behind barriers of time and distance that dwarf human scales. Webb will continue observing, more data will emerge. Some nearby systems may yet surprise us with evidence of atmospheric retention or unexpected chemical signatures. The telescope's mission extends for years. Hundreds of exoplanets will pass through its observational crosshairs. Statistical patterns will emerge from the accumulating data, but the early results establish a baseline expectation that our nearest neighbours are unlikely to offer refuge. The pattern of atmospheric stripping on red dwarf planets appears robust. The physics driving that stripping operates universally. Stars throughout the galaxy follow the same rules. Red dwarfs everywhere flare with the same violence. Their planets everywhere face the same erosion. The stars that seemed so close were never as welcoming as we imagined. The cosmic neighbourhood we thought we understood is revealing itself as hostile territory, where Earth-like conditions cannot persist. Our models painted pictures of possible oceans and alien sunsets. Webb is showing us bare rock and stellar radiation. This is not the end of the search for habitable worlds. It is a recalibration of expectations. The next sections will explore why red dwarf violence proves so devastating, what chemical signatures reveal about nearby planetary conditions, and how far we must ultimately look to find worlds where life might thrive. The local habitability illusion collapse has only begun. What comes next makes the picture even grimmer. Look up at the night sky and find the brightest star visible from your location. Whatever stellar beacon draws your eye, odds are excellent that you are not looking at the most common type of star in our galaxy. The stars bright enough for human eyes to see represent a tiny fraction of the stellar population. They are the giants and supergiants, the nearby sun-like stars, the exceptional cases that outshine their countless smaller neighbours. The universe favours a different kind of star. Red dwarfs dominate every stellar census astronomers conduct. These small, cool furnaces burn with a fraction of our sun's luminosity. They are so dim that not a single red dwarf is visible to the naked eye from Earth, despite the nearest one sitting just 4.2 light-years away. Proxima Centauri, our closest stellar neighbour, requires telescopic observation to detect. Among the 20 nearest star systems to Earth, 14 contain red dwarfs. The stellar neighbourhood is red dwarf territory. This numerical dominance carries profound implications for planetary habitability. If red dwarfs make up the majority of stars, and if most stars host planetary systems, then red dwarf planets represent the most common real estate in our galaxy. Any assessment of cosmic habitability must grapple with the question of whether these abundant worlds can support life. For years, that question received optimistic answers. Red dwarf stars offered theoretical advantages that sun-like stars could not match. Their extraordinary longevity once seemed promising for life development, but James Webb Space Telescope and supporting observatories are revealing why this longevity may be worthless. Red dwarf stars do not burn peacefully. They rage. The stellar violence of M-dwarf stars begins with flares. Our sun produces solar flares that occasionally disrupt satellite communications and create aurora displays at high latitudes. These events release energy equivalent to billions of hydrogen bombs detonating simultaneously. They are impressive by human standards, but modest by stellar ones. Red dwarf flares operate on a completely different scale. Proxima Centauri produced a flare in 2019 that briefly increased the star's brightness by more than 1,000 times at ultraviolet wavelengths. The energy released exceeded the most powerful solar flares ever recorded by factors of several hundred. This was not an exceptional event. It was a typical flare from a typical red dwarf. The physics behind red dwarf flaring explains why these small stars behave so violently. Red dwarfs are fully convective, meaning their entire stellar mass participates in the churning motion that transports heat from core to surface. Our Sun, by contrast, has a radiative zone between its core and its convective outer layer. In a fully convective star, magnetic field lines twist and tangle throughout the entire stellar volume. These tangled fields store enormous amounts of energy. When field lines reconnect, that stored energy releases explosively as flares. The process resembles a rubber band stretched to its breaking point. The snap releases all the tension at once. Red dwarfs snap constantly. Webb observations, combined with data from other instruments, reveal that red dwarf flaring occurs with disturbing frequency. Studies monitoring the star have recorded dozens of significant flare events per year, with smaller flares occurring almost daily. Over geological timescales, this translates to billions of sterilizing events, bombarding any planets in close orbit. Consider what a billion flare events means for atmospheric retention. Each flare bathes nearby planets in extreme ultraviolet radiation and X-rays. This radiation does not simply warm planetary surfaces. It interacts with atmospheric molecules in ways that drive permanent chemical and physical changes. When extreme ultraviolet photons strike atmospheric gases, they ionize atoms by stripping away electrons. The resulting charged particles behave differently than neutral atoms. They respond to magnetic fields. They can be accelerated to escape velocity by electromagnetic forces. They leave the planet entirely, carrying away atmospheric mass that can never be recovered. A single flare may strip away only a tiny fraction of a planet's atmosphere. The loss might be measured in kilograms or tons, rather than the billions of tons that constitute a substantial atmospheric envelope. But compound that loss over billions of flares spanning billions of years, the cumulative effect is catastrophic. Planets that may have started with substantial atmospheric envelopes find themselves gradually exposed to the vacuum of space. The TRAPPIST-1 system provides a laboratory for observing this process at work. Webb's detection of minimal atmospheres on the inner planets aligns perfectly with models predicting continuous atmospheric erosion from red dwarf activity. These worlds orbit close enough to their star that every flare delivers maximum damage. Over the 4 to 7 billion years since the system formed, the accumulated losses have left these planets stripped bare. But the stripping rate depends critically on orbital distance. Radiation intensity decreases with the square of distance from the source. A planet orbiting twice as far from its star receives only 1/4 the radiation exposure. This inverse square relationship suggests that planets in the outer reaches of red dwarf systems might escape the worst damage. The cruel physics of red dwarf habitable zones eliminates this escape route. These dim stars produce so little light and heat that their habitable zones sit extremely close to the stellar surface. TRAPPIST-1's habitable zone spans orbital distances between roughly 3 and 7 million miles. For comparison, Mercury orbits our Sun at 36 million miles and still experiences surface temperatures exceeding 800 degrees Fahrenheit. Planets in red dwarf habitable zones cannot escape to safer distances. Moving outward means moving into regions too cold for liquid water. The same orbital proximity that provides habitable temperatures also delivers maximum radiation exposure. There is no safe distance that remains warm enough for Earth-like conditions, but flares represent only part of the stellar assault. Red dwarf stars also produce powerful coronal mass ejections that make solar equivalents look gentle. These events expel billions of tons of stellar material at speeds approaching a significant fraction of light speed. When this material impacts a planetary atmosphere, it can compress magnetic field lines and directly strip away atmospheric gases. A coronal mass ejection is not simply hot gas expanding outward. It is a coherent structure of magnetized plasma carrying its own magnetic field configuration. When this structure encounters a planet, the interaction depends on how the planetary and stellar magnetic fields align. Under certain configurations, the stellar field can reconnect with the planetary field, opening pathways for atmospheric escape that would otherwise remain closed. Our Sun produces coronal mass ejections regularly. The most powerful events can disrupt power grids and satellite operations when they impact Earth's magnetosphere, but Earth's orbital distance provides substantial protection. Most solar coronal mass ejections miss our planet entirely because they emerge from localized regions on the solar surface and spread outward in cones that may not intersect Earth's position. Planets in tight orbits around red dwarfs face far worse odds. Their close proximity to the star means that a larger fraction of stellar activity intersects their orbital path. A coronal mass ejection that would miss Earth entirely might score a direct hit on a planet orbiting at 4.5 million miles. The geometry of close orbits dramatically increases impact frequency. Recent modeling using data from Webb and other observatories suggests that planets orbiting in red dwarf habitable zones may experience coronal mass ejection impacts thousands of times more frequently than Earth. Each impact delivers atmospheric damage that compounds over cosmic time. Even planets with initially strong magnetic fields may find their protective barriers overwhelmed by the sheer rate of bombardment. This raises the critical question of magnetic field strength on exoplanets. Earth's magnetic field deflects much of the solar wind and shields our atmosphere from direct erosion. Without this invisible shield, our planet might have lost its atmosphere billions of years ago, becoming as barren as Mars. The geodynamo process that generates Earth's magnetic field requires specific conditions. A liquid metallic core must exist to conduct electrical currents. Convection within that core must be vigorous enough to sustain the dynamo process. The planet's rotation provides additional energy input that organizes the magnetic field into a coherent dipole structure. Planets in red dwarf systems face compounded challenges in generating protective magnetic fields. Tidal locking, which occurs when a planet orbits close enough to its star that gravitational forces halt its rotation, affects the internal dynamics that drive magnetic field generation. Earth's magnetic field arises from convection currents in its liquid iron core, driven partly by the planet's rotation. A tidally locked world with no rotation may struggle to generate comparable field strength. The physics of tidal locking operates through gravitational gradients. Any extended body experiences stronger gravitational pull on its near side than its far side. This differential creates tidal bulges that the planet's rotation carries out of alignment with the star. The resulting torque gradually slows the planet's rotation until one face permanently points toward the star. For planets in red dwarf habitable zones, tidal locking occurs rapidly. The close orbital distances and strong gravitational gradients ensure that these worlds stop rotating within millions of years of formation. By the time any primordial atmosphere might establish conditions for life, the planet has already lost the rotational energy that might drive a protective magnetic field. Some planetary scientists argue that tidal locking does not necessarily prevent magnetic field generation. Alternative dynamo mechanisms might operate in slowly rotating or non-rotating worlds. Heat flow from a planet's interior could drive convection patterns that generate fields without requiring rotational input. Computer models suggest that such fields might be weaker and less organized than Earth's dipole, but could still provide some atmospheric protection. Webb cannot directly measure exoplanet magnetic fields. No telescope can. Magnetic fields are invisible to electromagnetic observation at interstellar distances. Their presence can only be inferred from secondary effects like radio emissions from charged particle interactions or the retention of atmospheres that would otherwise be stripped away. The absence of atmospheres on nearby red dwarf planets provides indirect evidence that magnetic protection is insufficient to counteract stellar violence. Whatever fields these worlds possess, they have proven inadequate to prevent atmospheric stripping over billions of years. The theoretical possibility of alternative dynamo mechanisms offers no comfort when observations show bare rock where oceans should flow. All of this still fails because the fundamental problem cannot be solved through planetary properties alone. Red dwarf stars that dominate our stellar neighborhood are not friendly hosts for life. Their longevity counts for nothing if their activity strips away the atmospheric protection necessary for liquid water and complex chemistry. The magnetosphere weakness observed indirectly through atmospheric absence creates a cascading failure of habitability requirements. Without an atmosphere, liquid water cannot exist on a planetary surface regardless of temperature. The boiling point of water depends on atmospheric pressure. At zero pressure, water sublimates directly from ice to vapor without passing through a liquid phase. Even if temperatures fall within the nominal habitable range, bare rock cannot support liquid oceans. Without liquid water, Earth-like biochemistry becomes impossible. Every known life form requires liquid water as a solvent for chemical reactions. Water's unique properties enable the molecular interactions that define biology. Alternative biochemistries based on other solvents remain purely theoretical. The absence of water eliminates the chemical foundation for life as we understand it. Without the protective layer of gases filtering stellar radiation, any surface biology would face constant exposure to sterilizing ultraviolet and X-ray bombardment. Earth's atmosphere absorbs most ultraviolet radiation before it reaches the surface. Remove this protection, and solar radiation would sterilize Earth's surface within hours. Red dwarf planets face radiation environments far more extreme than what Earth would experience without an atmosphere. The flare activity that strips atmospheres also delivers radiation doses that would destroy organic molecules. Even if liquid water somehow persisted on these worlds, the chemical building blocks of life could not survive the constant bombardment. Consider what this means for the planets orbiting Proxima Centauri. This star, our closest stellar neighbor, is a red dwarf exhibiting all the violent characteristics typical of its stellar class. Proxima Centauri b orbits within the habitable zone, but that designation assumed atmospheric conditions that increasingly appear not to exist. A bare rock exposed to Proxima Centauri's flaring activity would experience surface radiation levels thousands of times higher than Earth's surface receives. The radiation environment on Proxima Centauri b during a major flare event would exceed the lethal dose for most known organisms within minutes. The extreme ultraviolet flux alone would break apart complex molecules. X-ray exposure would damage cellular structures beyond any possibility of repair. Whatever survived, the radiation would face temperature extremes between the permanent day side and permanent night side that no Earth-based life could tolerate. The situation resembles a cruel cosmic joke. Red dwarf habitable zones sit close to the star because these dim furnaces produce limited light and heat. But this proximity places planets in the danger zone for stellar activity. The same closeness that provides appropriate temperatures also delivers maximum radiation damage. This proximity problem has no solution within the physics of red dwarf systems. You cannot move a planet to a safer distance without also moving it out of the temperature range where liquid water could exist. The habitable zone and the radiation danger zone overlap completely. Every planet warm enough for water is also close enough for sterilization. Sun-like stars offer a different geometry. Their habitable zones sit farther from the stellar surface, providing more buffer distance from flares and coronal mass ejections. Earth orbits roughly 93 million miles from the Sun. Proxima Centauri b orbits roughly 4.5 million miles from its star. The difference in exposure to stellar violence follows the inverse square law. Earth receives roughly 400 times less radiation per flare event than a planet at Proxima Centauri b's orbital distance would receive from an equivalent flare. But the comparison understates Earth's advantage, because solar flares are far less powerful than red dwarf flares to begin with. Combining the lower flare intensity with the greater orbital distance yields a radiation environment thousands of times more benign than what red dwarf planets experience. Earth's position represents a sanctuary that red dwarf worlds cannot access, but here lies another problem that compounds the local habitability illusion collapse. The nearest truly sun-like star with confirmed planets in its habitable zone lies much farther than our closest red dwarf neighbours. This distribution reflects the physics of star formation. Molecular clouds that collapse to form stars tend to fragment into many small pieces rather than a few large ones. Small fragments produce small stars. The mass distribution of newborn stars follows a power law that strongly favours low-mass objects. For every star, like our Sun, that forms, roughly a dozen red dwarfs emerge from the same stellar nursery. The abundance of red dwarfs once seemed like good news for habitability. More stars meant more planets. More planets meant more chances for life. The galaxy appeared to offer countless opportunities for biology to emerge on worlds orbiting these long-lived stellar furnaces. Webb's observations reveal that abundance counts for nothing when every abundant system proves hostile. The galaxy may contain hundreds of billions of red dwarf planets, but if none of them can retain atmospheres, that abundance represents not opportunity but cosmic irony. The most common real estate in the universe appears to be universally uninhabitable. This distribution compounds the local habitability illusion collapse. Not only are red dwarf planets proving hostile to life, but the alternative stellar hosts are much more distant than the optimistic narrative suggested. The nearest safe harbour may require crossing far greater distances than missions to Proxima Centauri would demand. The X-ray emission from red dwarf stars deserves particular attention because it operates continuously rather than episodically. Flares represent dramatic bursts of activity, but even quiescent red dwarfs produce X-ray emission that exceeds solar levels by substantial factors. The coronae of red dwarf stars maintain temperatures exceeding 1 million degrees Celsius. This superheated plasma emits X-rays continuously as electrons interact with ions in the coronal gas. The X-ray luminosity of a typical red dwarf exceeds our Sun's X-ray output by factors ranging from 10 to 100, depending on the star's age and activity level. Planets in red dwarf habitable zones receive this elevated X-ray flux constantly, not just during flare events. The continuous bombardment drives atmospheric chemistry in directions incompatible with life. Water molecules break apart under X-ray exposure. Ozone, which might otherwise protect planetary surfaces, cannot form in sufficient quantities when X-rays continuously destroy it. Webb's spectroscopic observations of red dwarf planetary atmospheres show the chemical consequences of this X-ray environment. Where atmospheres exist at all, they show compositions dominated by molecules that survive under radiation stress. The complex organic chemistry that might precede life cannot establish itself under constant X-ray bombardment. Young red dwarfs present even worse conditions than mature ones. All stars are more active when young, but red dwarfs remain in their hyperactive youth phase for extended periods. A red dwarf of roughly 1/10 solar mass requires approximately 100 to 200 million years to settle onto the main sequence and begin its stable hydrogen-burning phase. During this extended adolescence, the star's luminosity varies dramatically. Its flare rate exceeds even the elevated levels of mature red dwarfs, and its X-ray emission peaks at values that would strip Earth's atmosphere within geological instants. Any planet forming in a red dwarf system must survive this prolonged bombardment before conditions even begin to stabilize. The primordial atmosphere, delivered by volcanic outgassing and cometary impacts, faces continuous erosion throughout this extended hostile phase. By the time the star calms down, whatever atmosphere the planet started with may be long gone. Webb's continued observations of red dwarf systems will refine our understanding of how universal atmospheric stripping is among these stellar hosts. Some variation in stellar activity levels exists. Not all red dwarfs flare with equal ferocity. Some may prove calmer than others, potentially allowing atmospheric retention on well-positioned planets. The search for calm red dwarfs has occupied planetary scientists for years. These hypothetical quiet stars would offer the longevity advantages of red dwarfs without the sterilizing activity. Their planets might retain atmospheres and support liquid water despite the close orbital distances required for habitable temperatures. But the early returns from Webb observations are not encouraging. System after system shows evidence of planetary surfaces exposed directly to stellar radiation. The pattern suggests that atmospheric erosion is the default outcome for red dwarf planets, not the exception. Calm red dwarfs, if they exist, appear to be rare enough that none have yet appeared in nearby space. The physics of red dwarf structure explains why calm examples might be fundamentally rare. The fully convective interiors of these stars guarantee vigorous magnetic activity. Unlike Sun-like stars where only the outer layers convect, red dwarfs churn throughout their entire volume. This structural feature that enables their trillion-year lifespans also ensures their violent behavior throughout those extended lives. Some theoretical models propose that red dwarfs gradually calm with extreme age. Stars that have burned for hundreds of billions of years might exhaust whatever internal processes drive magnetic activity. Their planets might finally experience conditions suitable for atmospheric retention and biological development. But the universe is only 13.8 billion years old. No red dwarf has yet reached the extreme age where this hypothetical calming might occur. The oldest red dwarfs in existence are still young by the standards of their potential lifespans. Whatever tranquility the far future might bring, no planet in the present universe can benefit from it. This brings us back to the real problem that dominates this investigation. The stars nearest to Earth are precisely the wrong kind of stars for hosting habitable worlds. Their abundance is irrelevant if their activity levels prevent the conditions necessary for life. Red dwarf longevity means nothing when that extended lifetime is spent continuously stripping atmospheres from companion planets. The stellar violence Webb is documenting was predicted by models, but the direct observational confirmation carries different weight. Predictions can be questioned, assumptions can be revised, theoretical frameworks can be debated, but measurements of absent atmospheres and calculations of flare frequencies leave little room for alternative interpretations. The data shows what exists: bare planetary surfaces where models once predicted possible oceans, radiation environments where models once hoped for temperate conditions, atmospheric stripping where models once assumed atmospheric retention. Each observation narrows the range of plausible interpretations toward the pessimistic end of previous estimates. Our closest stellar neighbors are killing their planetary children through sustained violence that began when these systems formed and continues to this day. The worlds we hoped might offer refuge from our cosmic isolation are being slowly destroyed by their parent stars. It is a process operating over billions of years, invisible to any single observation, detectable only through the accumulated evidence of its completion. The TRAPPIST-1 planets did not lose their atmospheres in dramatic events. They lost them molecule by molecule, ion by ion, across timescales that dwarf human history. The violence was patient. The destruction was gradual. The result was absolute. This reality forces a fundamental reassessment of interstellar ambitions. The nearest stars are not destinations worth reaching. Their planets offer nothing but radiation-blasted wastelands where no atmosphere softens the stellar assault. If humanity seeks habitable real estate beyond our solar system, we must look past the red dwarf zone that dominates our local stellar environment. The search continues. Webb will examine more systems. Some may prove less hostile than the early examples. Statistical analyses will eventually reveal whether any red dwarf systems buck the trend, retaining atmospheres despite the stellar violence their planets endure. But the baseline expectation has shifted dramatically. Red dwarf habitability was always questioned by careful scientists. Theoretical concerns about flare activity and atmospheric erosion appeared in the scientific literature for decades before Webb launched. The optimistic models that captured public imagination were not wrong about the physics. They were wrong about the balance of competing processes. Atmospheric erosion competes with volcanic replenishment. Magnetic shielding competes with stellar bombardment. The models allowed for outcomes where retention won these competitions. The observations show that erosion and bombardment win instead. The stars that seemed most accessible are proving most deadly. Our nearest neighbours in space are not welcoming hosts but violent destroyers. The local habitability illusion continues to collapse with each new observation, confirming that red dwarf planets orbit in perpetual danger. No matter how advanced our models become, they cannot change the physics of stellar activity. Their planets suffer because orbital mechanics places habitable temperatures in radiation danger zones. Atmospheres erode because the stripping processes operate faster than replenishment can match. The worlds that remain are bare rocks baking under stellar radiation, monuments to the violence that shaped them. This is not speculation, this is observation. Webb is showing us reality as it exists, not as we hoped it would be. The red dwarf planets closest to Earth have lost whatever chance they had for habitability. The stellar violence responsible continues unabated. And no technology humans might develop can change the fundamental physics that makes these systems hostile to life. The promise of nearby habitable worlds orbiting long-lived red dwarf stars has collapsed. What replaces that promise is a more sober understanding of the challenges facing any search for cosmic habitability. The stars must be right. For the worlds closest to Earth, the stars are wrong. Light carries secrets across the cosmos. Every photon arriving at Earth from a distant star has passed through space that may contain planets, atmospheres, gas clouds, and dust. Each interaction with matter leaves an imprint on the light spectrum. By analyzing which wavelengths are absorbed or altered during this cosmic journey, astronomers can determine the chemical composition of objects they will never visit in person. This technique predates modern astronomy by centuries. Isaac Newton first demonstrated that white light contains a rainbow of colors separable by a prism. In 1814, Joseph von Fraunhofer noticed dark lines crossing the solar spectrum where specific wavelengths were missing. By 1859, Gustav Kirchhoff and Robert Bunsen had determined that these absorption lines corresponded to specific chemical elements. Each element absorbs light at characteristic wavelengths, as unique as fingerprints. James Webb Space Telescope has transformed this ancient technique into an unprecedented tool for exoplanet investigation. Its infrared spectrographs achieve sensitivity levels that previous instruments could not approach. When a planet passes in front of its star as seen from Earth, a tiny fraction of starlight filters through the planet's atmosphere. Webb can detect which chemicals absorb which wavelengths during this transit, building a molecular inventory of alien air. The physics of transit spectroscopy relies on geometry and timing. As a planet crosses the face of its star, it blocks a small percentage of the star's light. The exact percentage depends on the relative sizes of planet and star. A Jupiter-sized planet orbiting a Sun-sized star might block 1% of the starlight. An Earth-sized planet might block only 1/100th of 1%, but the blocked light contains information beyond simple dimming. During transit, starlight passes through the thin shell of atmosphere surrounding the planet's silhouette. This light picks up absorption signatures from whatever gases that atmosphere contains. Carbon dioxide creates its own characteristic absorption pattern. Methane, oxygen, nitrogen, ammonia, each molecule writes its signature in missing wavelengths. Webb's position in space eliminates the atmospheric interference that plagues ground-based spectroscopy. Earth's own atmosphere contains water vapor, carbon dioxide, and other molecules that absorb the same wavelengths astronomers hope to detect on exoplanets. Observing from space provides a clean baseline against which extraterrestrial atmospheric signatures can be measured. The results emerging from Webb's first years of operation tell a story far different from what habitable zone designations implied. Consider what we expected to find on temperate exoplanets. Water vapor should be common on worlds where liquid water might exist. The presence of surface oceans would guarantee atmospheric water through constant evaporation. Even worlds with subsurface water might outgas enough vapor to leave detectable signatures. Water represented the primary target for habitability searches. Methane could indicate biological activity or geological processes that recycle carbon. On Earth, most atmospheric methane comes from biological sources. Microorganisms in wetlands, digestive systems of ruminant animals, rice paddies, and landfills all release methane as metabolic byproducts. Geological processes can also produce methane through reactions between water and certain rock types. Finding methane would not prove life exists, but it would indicate active chemistry worth investigating further. Oxygen, while not guaranteed, might point toward photosynthesis or other mechanisms that build up reactive gases. Earth's oxygen-rich atmosphere represents a biological fingerprint visible from space. Photosynthetic organisms split water molecules, releasing oxygen as a waste product. Over billions of years, this biological output transformed Earth's atmosphere from oxygen-poor to oxygen-rich. Detecting oxygen on an exoplanet would trigger intense scrutiny of possible biological origins. Carbon dioxide should be present as part of carbon cycle processes that regulate planetary climate. Earth maintains a delicate balance, where volcanic outgassing releases carbon dioxide while weathering and ocean absorption remove it. This cycle moderates temperature fluctuations over geological time. Finding carbon dioxide in moderate concentrations would suggest active geological and chemical processes consistent with planetary habitability. The search for biosignatures followed a carefully designed hierarchy. Astronomers developed detection priorities based on which molecules would be most significant and most detectable given Webb's capabilities. Water vapor sat at the top of this hierarchy. Its presence would indicate either surface oceans undergoing evaporation or active hydrological cycles redistributing moisture through atmospheric circulation. Water detection would not prove habitability, but its absence would effectively rule it out. No known biochemistry operates without liquid water as a solvent. Carbon dioxide occupied the second tier. Moderate concentrations would suggest geological activity releasing volcanic gases balanced by removal processes that prevent runaway accumulation. The specific concentration mattered enormously. The difference between Earth's trace amounts and Venus's crushing abundance marks the boundary between habitable and hellish. Methane represented a particularly exciting target because of its instability. Detecting methane would therefore indicate active production, either geological or potentially biological. Finding methane on an exoplanet would demand explanation. Oxygen and ozone form the most tantalizing tier. These molecules are so reactive that their sustained presence typically requires continuous production. Earth's oxygen-rich atmosphere exists only because photosynthetic organisms constantly replenish what chemical reactions would otherwise consume. Detecting oxygen on a rocky exoplanet would trigger immediate investigation of possible biological origins. The detection hierarchy also included molecules that would indicate uninhabitable conditions. Sulfur dioxide in high concentrations would suggest volcanic hellscapes. Carbon monoxide would indicate atmospheric chemistry incompatible with Earth-like biology. Ammonia at certain concentrations might suggest reducing atmospheres unlike anything that supports life as we understand it. Scientists designed observation campaigns around this hierarchy. Webb would first search for water, the foundation of habitability. Positive detection would justify deeper investigation for other biosignature candidates. Negative detection would suggest moving to other targets rather than investing additional observation time. The hierarchy assumed that nearby rocky planets would show diverse atmospheric compositions. Some would lack atmospheres entirely. Others might show Venus-like runaway conditions, but statistical expectations suggested that at least some fraction would display the water-rich, moderate signatures associated with potentially habitable conditions. Webb's observations are systematically eliminating candidates from the promising categories while populating the hostile categories. The biosignature hierarchy remains valid as a detection framework, but the nearby planets being observed fall consistently into the categories, indicating uninhabitable conditions rather than the categories suggesting biological potential. What Webb is actually finding on nearby exoplanets defies these expectations in troubling ways. Transit spectroscopy of several TRAPPIST-1 planets has revealed effectively featureless spectra in the infrared wavelengths, where atmospheric signatures should appear most prominently. This flatline result indicates one of two possibilities. Either these worlds possess no substantial atmospheres to leave spectral imprints, or they are shrouded in high-altitude hazes that block deeper atmospheric observation. The distinction matters for understanding what these worlds might look like up close. An airless planet presents a surface exposed directly to space. No weather exists because weather requires an atmosphere to move. No sound propagates because sound requires a medium to carry vibrations. Temperature differences between day and night side reach extreme values because no atmospheric circulation redistributes heat. A haze-shrouded world presents different but equally hostile conditions. The hazes that block spectral observation form through photochemical processes where stellar radiation breaks apart simple molecules, allowing their fragments to recombine into complex organic compounds. These compounds aggregate into tiny particles suspended in the upper atmosphere. Titan, Saturn's largest moon, provides a solar system example. Its haze layer obscures the surface so completely that cameras cannot see through it. Neither possibility supports habitability. An absent atmosphere obviously precludes Earth-like surface conditions. A haze-dominated atmosphere suggests chemical regimes unlike anything that supports life as we understand it. The hazes themselves may be composed of organic molecules, but organic does not mean biological. The same photochemistry that creates atmospheric hazes would destroy any unprotected biological molecules attempting to function beneath them, but the absence of expected molecules tells only part of the story. What Webb has detected on some exoplanets proves equally illuminating about the hostile conditions prevalent in nearby space. Webb's first detailed atmospheric characterization of an exoplanet came from WASP 39b, a hot gas giant orbiting a star roughly 700 light-years from Earth. While not a rocky world and far too hot for habitability, this planet demonstrated Webb's spectroscopic capabilities in unprecedented detail. Webb detected sulfur dioxide in WASP 39b's atmosphere. This discovery marked the first time this molecule had been identified on an exoplanet. Sulfur dioxide detection indicates active photochemistry driven by stellar radiation. The molecule forms when stellar ultraviolet light triggers chemical reactions in the upper atmosphere, combining sulfur from the planet's interior with oxygen in ways that require intense radiation to proceed. The sulfur dioxide detection on WASP 39b established proof of concept. Webb could identify specific molecules in exoplanet atmospheres with sensitivity previous instruments could not achieve. The technique works. The question became what Webb would find when turned towards smaller rocky worlds closer to Earth. The answers have proven troubling. Webb turned toward rocky planets in nearby red dwarf systems and found results that undermine habitability hopes. GJ 486b, a rocky super-Earth, orbiting a red dwarf approximately 26 light-years from Earth, became one of Webb's early targets for rocky world atmospheric characterization. This planet offered excellent conditions for observation. It transits its star frequently, allowing multiple observations to build signal strength. Its relatively large size for a rocky world creates a measurable atmospheric signature if any atmosphere exists. Initial Webb observations detected hints of water vapor in GJ 486b's spectrum. The discovery sparked cautious excitement. Water on a nearby rocky world would be exactly the signature habitability researchers sought. Even a small amount of atmospheric water would indicate conditions dramatically different from the bare rocks observed in the TRAPPIST-1 system. But subsequent analysis revealed a troubling ambiguity. The water vapor signature might not originate from the planet at all. Red dwarf stars have cool outer regions called star spots that contain water vapor in their upper atmospheres. When GJ 486b transits across star spots, the stellar water vapor can mimic a planetary atmospheric signature. Distinguishing between planetary water and stellar contamination requires careful analysis that remains ongoing. This ambiguity itself tells a story. Even when promising signals appear, they may not indicate the habitable conditions we hope to find. The search for water on nearby rocky worlds has not yielded clean detections that confirm atmospheric retention and surface habitability. Instead, it has revealed the complexity of atmospheric characterization and the multiple ways that signals can mislead. TRAPPIST-1c provided another critical data point. This world, positioned at the inner edge of its star's habitable zone, represented a key test case for atmospheric retention around red dwarf planets. Webb's thermal emission observations revealed surface temperatures consistent with a bare rock, lacking significant atmospheric pressure. Whatever atmosphere this planet may have once possessed has been stripped away by billions of years of stellar bombardment. The pattern extends across multiple targets. Rocky planets orbiting nearby red dwarfs show either no detectable atmospheres or ambiguous signals that resist interpretation as habitable conditions. The chemical inventory Webb expected to find, water vapor, moderate carbon dioxide, perhaps traces of methane, remains absent from the nearby planetary census. All of this still fails because the chemical signatures Webb detects reveal environments fundamentally incompatible with life. Finding an atmosphere is not enough. Finding water vapor would be encouraging but insufficient alone. The entire chemical package must align with conditions that support liquid water, stable temperatures, and the molecular building blocks of biology. The disk instability signatures Webb observes in young planetary systems provide clues to why nearby mature systems show such hostile chemistry. Planetary formation involves violent processes that determine initial compositions. Worlds that form in different regions of protoplanetary disks inherit different chemical inventories. Protoplanetary disks are not uniform chemical environments. Temperature gradients from inner to outer disk create frost lines where volatile compounds transition from gas to solid phase. Interior to the water frost line, water exists as vapor and cannot incorporate into forming planetesimals. Exterior to this line, water ice condenses onto dust grains and becomes part of the solid material that assembles into planets. The water frost line in disks around red dwarf stars sits closer to the star than equivalent lines around sun-like stars. Lower stellar luminosity means lower disk temperatures at any given distance. This geometry might seem advantageous for planet formation because it places the frost line within the habitable zone rather than beyond it. But Webb's observations of young red dwarf systems reveal complications that challenge this optimistic interpretation. The intense flare activity that characterizes young red dwarfs heats the inner disk episodically. During major flare events, the frost line moves outward dramatically. Water ice that accumulated during quiet periods sublimates and escapes the disk entirely. This volatile pumping process depletes the inner disk of water over millions of years of planet formation. Rocky planets assembling in these regions inherit water-poor compositions, regardless of where the frost line nominally sits during quiet phases. The finished planets contain less water than their distance from the frost line would suggest because flare activity removed water during their formation. Webb's observations of debris disks around mature red dwarfs show the consequences of this depletion. The dust composition in these disks reflects the makeup of asteroid belt analogues that feed the debris through collisions. Red dwarf debris disks show systematically different compositions than comparable disks around sun-like stars. The water signatures that appear prominently in solar-type debris disks are muted or absent around red dwarfs. This formation chemistry compounds the atmospheric stripping problem discussed in earlier sections. Planets may form with less water than Earth possessed initially. They then lose whatever water they did inherit through billions of years of stellar bombardment. The end result is worlds that never had a chance at habitability, regardless of their position relative to stellar habitable zones. The carbon dioxide paradox adds another layer to this chemical story. Webb has detected carbon dioxide atmospheres on several exoplanets, including some that occupy positions near stellar habitable zones. Carbon dioxide is a greenhouse gas that can warm planetary surfaces above what stellar radiation alone would achieve. This warming effect led some researchers to suggest that carbon dioxide atmospheres might compensate for diminished stellar heating on planets near the outer edge of habitable zones. Venus maintains surface temperatures exceeding 800 degrees Fahrenheit, partly through its dense carbon dioxide atmosphere. The greenhouse effect traps infrared radiation attempting to escape to space. Surface heat cannot radiate away efficiently, so temperatures rise until the planet reaches thermal equilibrium at a much higher temperature than a bare rock would maintain. But carbon dioxide alone does not create habitability. Without water to moderate the carbon cycle, carbon dioxide can accumulate to crushing atmospheric pressures. Earth maintains livable carbon dioxide levels because multiple processes remove the gas as fast as volcanoes release it. Weathering reactions dissolve carbon dioxide in rainwater to form carbonic acid that attacks silicate rocks. Marine organisms incorporate dissolved carbon into shells that eventually become limestone. Plants fix atmospheric carbon into organic compounds through photosynthesis. All these removal processes require liquid water. Weathering needs rain. Marine organisms need oceans. Plants need water for photosynthesis. Without water, carbon dioxide released by volcanoes accumulates indefinitely. The greenhouse effect strengthens continuously. Surface temperatures rise until the planet reaches a new equilibrium far too hot for liquid water, even if water were somehow present. This runaway greenhouse scenario transforms potentially habitable worlds into Venus analogues. The process is self-reinforcing because higher temperatures drive any remaining water into the atmosphere, where photodissociation destroys it permanently. Once the runaway begins, no natural process can reverse it. Webb's detection of carbon dioxide on nearby exoplanets without accompanying water signatures suggests runaway greenhouse scenarios rather than temperate conditions. The carbon dioxide indicates active volcanism releasing greenhouse gases. The absent water indicates that no moderating processes limit greenhouse accumulation. These worlds are hot and getting hotter, their atmospheres thickening with each volcanic eruption. The specific carbon dioxide concentrations Webb detects support this interpretation. Earth's atmosphere contains roughly 420 parts per million of carbon dioxide. Venus contains approximately 96% carbon dioxide, nearly pure. Webb's measurements of exoplanet atmospheres show carbon dioxide abundances closer to Venusian than terrestrial levels. These are not worlds with mild greenhouse warming. They are worlds undergoing or completing runaway greenhouse transformations. The absence of methane proves equally significant for habitability assessment. Methane should accumulate in atmospheres where geological or biological processes release it, and where ultraviolet radiation is insufficient to break it down quickly. On Earth, methane persists in the atmosphere for roughly 9 to 12 years before oxidation destroys it. The current atmospheric concentration of about 1.9 parts per million represents equilibrium between continuous biological and geological release and continuous chemical destruction. Finding similar methane concentrations on an exoplanet would indicate active release processes competing with destruction. Such activity would be worth investigating regardless of whether the source proved biological or geological. Webb's systematic non-detection of methane on nearby temperate exoplanets fits the emerging pattern. These worlds lack the chemical signatures associated with habitable environments, The ultraviolet radiation environment around red dwarf stars destroys methane far more rapidly than solar radiation destroys it around Earth. Any methane release would require improbably high rates to maintain detectable atmospheric concentrations. But the deeper implication concerns the absence of methane sources. Geological methane production on Earth occurs primarily through serpentinization reactions, where water reacts with certain iron-rich rocks. Without water, these reactions cannot proceed. Biological methane production requires living organisms with metabolic pathways that release methane as a byproduct. Without life, these sources do not exist. The absent methane on nearby exoplanets suggests that neither geological nor biological methane sources operate on these worlds. This absence corroborates the missing water detections. Worlds without water cannot support serpentinization. Worlds without life cannot support methanogenic biology. The chemical inventory tells a consistent story of uninhabitable conditions. This chemical devastation extends to the surfaces of atmosphereless worlds. Without atmospheric protection, planetary surfaces experience direct exposure to stellar wind particles and cosmic radiation. Rock chemistry changes under these conditions in ways that render surfaces hostile to organic molecules. When charged particles from stellar winds strike unprotected rock surfaces, they implant themselves into the upper rock layers. Over billions of years, this bombardment alters surface mineralogy in measurable ways. The implanted particles react with rock constituents, oxidizing iron-bearing minerals and creating chemically reactive surface layers. Mars provides a solar system example of this surface modification. The Viking landers in 1976 found Martian soil highly reactive toward organic compounds. Laboratory simulations suggested that peroxide compounds formed through radiation exposure created this reactivity. Any organic molecules placed in contact with Martian soil decomposed rapidly through oxidation reactions. The same surface oxidation processes operating on airless red dwarf planets would create even more hostile conditions. The radiation flux exceeds what Mars experiences by orders of magnitude. The oxidation would proceed faster and penetrate deeper. Surface layers would become chemical traps that destroy organic molecules on contact. This surface chemistry matters for habitability, because life requires organic molecules to persist long enough for biological processes to operate. DNA, proteins, lipid membranes, all the molecular components of cells contain organic chemical bonds. These bonds break readily under oxidizing conditions. Life cannot establish itself on surfaces that destroy its chemical foundations. Webb cannot directly observe exoplanet surface chemistry because transit spectroscopy samples only atmospheric layers, but the atmospheric observations constrain surface conditions through physical connections between air and ground. An atmosphereless world necessarily has an oxidized surface. A world with sulfur-dominated atmosphere necessarily has acidic surface conditions. The atmospheric chemistry Webb detects implies surface chemistry incompatible with biology. Webb's chemical inventory of nearby exoplanets continues to expand with each observing campaign. New targets enter the queue as orbital geometries create favorable transit opportunities. Improved analysis techniques extract more information from existing data. Noise reduction algorithms reveal subtle spectral features previously hidden in instrumental variations. But the pattern established by early observations shows remarkable consistency. Nearby rocky exoplanets do not display the chemical signatures expected from habitable worlds. Water is absent or ambiguous where it should be abundant. Methane is absent where active geology or biology might produce it. Carbon dioxide dominates where temperate conditions were predicted. The chemistry of devastation appears prevalent across the nearby red dwarf systems Webb has examined. This brings us back to the real problem that chemical observation confirms. The local habitability illusion collapse is not merely about absent atmospheres. It extends to the fundamental chemistry of nearby planetary systems. The molecular building blocks necessary for life appear absent from worlds where we hope to find them. The chemistry story corroborates and extends the physical story told by atmospheric absence and stellar violence. Each line of evidence points in the same direction. Nearby star systems are not refuges waiting for human exploration. They are hostile environments where the conditions necessary for life cannot persist. No matter how advanced our models become, they cannot create water on worlds that have lost it. They cannot transform sulfur dioxide atmospheres into breathable air. They cannot establish Earth-like chemistry on planets that formed with different compositions and evolved under hostile stellar radiation. The chemical signatures of devastation that Webb detects are not temporary conditions awaiting improvement. They are the permanent outcomes of billions of years of planetary evolution under red dwarf stellar environments. These worlds reached their current states through processes that operated irreversibly over cosmic time. They will not become habitable through any mechanism natural processes might provide. Formation depleted them of volatiles. Stellar bombardment stripped whatever volatiles remained. Runaway greenhouse processes transformed promising atmospheres into crushing toxic envelopes. Surface oxidation rendered rocks hostile to organic chemistry. Each process contributed to the final uninhabitable state. Each process was irreversible. This chemical reality forces recognition that habitable zone designations, based on temperature alone, wildly overestimated the frequency of genuinely habitable worlds. Position matters for determining equilibrium temperature, but chemistry matters for determining whether that temperature permits liquid water, stable atmospheres, and biological activity. The chemistry of nearby exoplanets is wrong for life in fundamental ways that temperature calculations cannot capture. The molecules Webb sought represented hope for biological relevance: water for solvent, methane for active chemistry, oxygen for biological signatures, carbon dioxide in moderate amounts for climate regulation. These molecular markers would have indicated environments where life might find purchase. Instead, Webb finds ambiguous water signals contaminated by stellar artifacts. Absent methane suggesting no active geological or biological cycling. Carbon dioxide at Venus-like concentrations, indicating runaway greenhouse conditions. Empty spectra, indicating no atmosphere at all. The chemical inventory of nearby space contains none of the molecules associated with habitable environments, and several molecules associated with conditions lethal to life. This chemical story will continue developing as Webb accumulates more observations. Some distant exoplanets may yet reveal promising signatures. Worlds orbiting calmer stars at greater distances may retain the volatiles their nearby counterparts have lost. The search for habitable chemistry has not ended with the collapse of local habitability illusions, but the search must now focus on more distant targets. The chemistry of nearby space is hostile. The molecules necessary for life are absent or ambiguous. The molecules present indicate deadly conditions. Webb spectroscopy has written the chemical epitaph for habitability hopes attached to our closest stellar neighbours. Picture Earth as a single house standing in an infinite desert. For decades, astronomers assured us that neighbouring houses stood just beyond the horizon. Proxima Centauri, TRAPPIST-1, dozens of red dwarf systems hosting rocky planets in their habitable zones. The cosmic neighbourhood seemed populated with potential destinations. Maps showed promising addresses. Statistical models counted doors waiting to be knocked upon. James Webb Space Telescope has walked us to the horizon and shown us what actually lies beyond. The neighbouring houses are ruins, burned shells, structures stripped of everything that made them habitable. The desert extends far beyond what optimistic models suggested. The addresses on our maps lead to wastelands. We must now reckon with a concept that restructures humanity's cosmic position. Call it the loneliness radius, the minimum distance from Earth to genuinely habitable worlds. This radius is expanding with every Webb observation, pushing potential destinations beyond the reach of any interstellar mission humanity could realistically undertake within timescales that matter for human civilization. The collapse of the local habitability illusion forces recalculation of everything we thought we knew about nearby cosmic real estate. Red dwarf systems that dominate our stellar neighborhood have proven hostile to atmospheric retention and Earth-like chemistry. The closest Sun-like stars with confirmed habitable zone planets lie considerably farther than the red dwarf systems that first captured public imagination. Consider the mathematics of interstellar travel under this new framework. Proxima Centauri, at 4.2 light-years, represented an ambitious but conceivable target. The breakthrough starshot concept demonstrated that this distance lay within theoretical reach. Laser-propelled craft, achieving 20% of light speed, could make the journey within 2 decades. Scientists who launched such probes might live to analyze returning data, but if Proxima Centauri's planets prove uninhabitable, and Webb's observations strongly suggest they are, where is the nearest viable destination? The answer may lie dozens of light-years away. Potentially habitable planets orbiting Sun-like stars exist at distances of 40, 60, perhaps 100 light-years from Earth. These systems avoid the red dwarf violence that strips atmospheres from close-orbiting worlds. Their habitable zones sit at distances where flare activity delivers far less damage than red dwarf companions experience. Their planets may retain the atmospheric protection and liquid water that nearby worlds have lost, but reaching these distant havens presents challenges that transform interstellar travel from difficult engineering into something approaching civilizational impossibility. The distance problem compounds in ways that simple multiplication fails to capture. A journey of 100 light-years at 20% of light speed requires 500 years. No human alive at launch would survive to see arrival. The mission becomes a multi-generational commitment, requiring social structures that have never been tested. Entire civilizations rise and fall over 5-century timescales. The Roman Empire lasted roughly 500 years from Augustus to Romulus Augustulus. The mission duration would span from the founding of Rome to its collapse. Even robotic probes face challenges that multiply with distance. Signal strength from transmitters decreases with the square of distance. A probe at 100 light-years would need to transmit with energy levels thousands of times higher than a probe at 4 light-years to deliver equivalent signal strength at Earth. The power requirements for such transmission may exceed what any probe could carry. Communication delays would stretch to centuries. A message sent from Earth would require 100 years to reach the probe. The response would take another 100 years to return. The scientists who sent the first command would be dust before the answer arrived. Their great-great-grandchildren's great-great-grandchildren would receive the reply. This temporal disconnection severs the feedback loop that makes exploration meaningful to individual humans. When Columbus sailed west, he returned within a year with news of what he found. When Apollo astronauts reached the moon, they reported back within seconds. Even the Mars rovers communicate with delays measured in minutes. Human psychology evolved for immediate feedback between action and consequence. The loneliness radius imposes delays that exceed human lifespan by factors that render personal investment meaningless. No one who participates in launching a mission to a star 100 light-years away will ever know whether it succeeded. The gratification, if any comes, belongs to descendants so distant they seem abstract rather than personal. Yet the physics admits no shortcuts. Light speed represents the absolute cosmic speed limit. No information, no matter, no spacecraft can exceed this barrier regardless of the energy applied or the technology employed. The universe enforces isolation through fundamental law rather than mere engineering difficulty. Some physicists speculate about exotic propulsion concepts that might circumvent these barriers. Warp drives that compress space ahead of a craft and expand it behind. Wormholes that tunnel through higher dimensions to emerge at distant locations. These concepts remain purely theoretical, with no experimental support and potentially insurmountable practical obstacles. Even if such technologies prove possible in principle, The energy requirements may exceed what any civilization could generate. Theoretical calculations for Alcubierre warp drives suggest power needs equivalent to converting Jupiter's entire mass into energy. Such requirements place these concepts beyond serious engineering consideration for the foreseeable future. The loneliness radius, therefore, represents not merely current technological limitation, but a fundamental constraint imposed by the structure of spacetime itself. We cannot simply build better engines and overcome distance. The universe does not permit the speeds that would make distant habitability accessible within human timescales. But perhaps the more profound implication touches the search for extraterrestrial intelligence. If habitable worlds cluster at greater distances than nearby star systems provide, then any intelligent species arising elsewhere faces the same isolation we do. Consider the probability calculations that SETI researchers employ. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors representing star formation rates, planetary abundance, habitability frequency, life emergence probability, intelligence, evolution likelihood, and civilization longevity. Previous estimates of habitability frequency assumed that planets in stellar habitable zones would generally retain atmospheres and support liquid water. This assumption yielded optimistic numbers, suggesting billions of potentially habitable worlds throughout the Milky Way. If even a tiny fraction developed intelligence and technology, the galaxy should teem with civilizations. Webb's observations forced dramatic downward revision of habitability frequency. Red dwarf planets that once counted as potentially habitable now appear hostile to life. The majority of stars in any given region are red dwarfs. The majority of rocky planets therefore orbit in radiation environments that strip atmospheres over cosmic time. The denominator of potentially habitable worlds shrinks enormously. This shrinkage has cascading effects through the Drake equation. Fewer habitable worlds mean fewer opportunities for life to emerge. Fewer life-bearing worlds mean fewer chances for intelligence to evolve. Fewer intelligent species mean fewer civilizations attempting communication. The collapse of nearby habitability hopes does not eliminate all candidates. It relocates them. Astronomers have identified potentially habitable worlds orbiting at distances that place them beyond the hostile red dwarf zone that dominates our immediate stellar neighborhood. Kepler 442b orbits a star approximately 112 light-years from Earth. This world sits squarely in its star's habitable zone and orbits a K-type star somewhat cooler than our Sun, but far more stable than red dwarfs. The star's reduced flare activity and the planet's greater orbital distance suggest conditions more favorable for atmospheric retention than anything in the TRAPPIST-1 system. Kepler 452b, sometimes called Earth's older cousin, orbits a Sun-like G-type star at a distance of approximately 1400 light-years. While too distant for detailed atmospheric characterization with current technology, this world demonstrates that Earth-sized planets in habitable zones around Sun-like stars do exist. They are simply far less common and far more distant than the red dwarf planets that dominate nearby space. The Tau Ceti system, roughly 12 light-years away, hosts several planet candidates, including worlds that might orbit within the habitable zone. Tau Ceti is a Sun-like star, offering the stability advantages that red dwarfs lack. However, the system contains a massive debris disk that would bombard inner planets with cometary impacts far exceeding what Earth experiences. Even this relatively nearby Sun-like system presents habitability challenges that complicate optimistic assessments. These distant candidates illustrate both the persistence of hope and its relocation beyond convenient reach. Habitable worlds may exist. They orbit stars stable enough to permit atmospheric retention. They formed in environments that allowed volatile incorporation, but they sit at distances measured in dozens or hundreds of light-years, rather than the single digits that characterized the red dwarf targets now proving hostile. Future space telescopes may eventually characterize atmospheres on these distant candidates. The proposed Habitable Worlds Observatory would directly image Earth-sized planets around nearby Sun-like stars, searching for the water vapor and oxygen signatures that would indicate genuine habitability. Such missions remain decades away from launch. Their targets remain decades of light travel away from Earth. The search for habitable worlds therefore continues, but with a transformed geography. The nearby systems that seemed most accessible have proven most hostile. The distant systems that might prove hospitable remain beyond detailed characterization and far beyond physical reach. The loneliness radius expands, not because habitable worlds cannot exist, but because they appear to exist only at distances that isolate them from humanity's practical aspirations. But the distance factor introduces additional isolation beyond mere numbers. Even if intelligent civilizations exist elsewhere in the galaxy, Webb's observations suggest they may be separated by distances that prevent meaningful contact. If habitable worlds orbited every star, civilizations separated by a few light years could exchange messages within individual lifetimes. A galactic civilization could theoretically emerge through gradual contact between neighboring inhabited systems. Information would flow, ideas would spread, cultures would intermingle across the stars. Webb's observations suggest a different architecture. Habitable worlds may be separated by distances measured in tens or hundreds of light years, rather than single digits. Contact between civilizations would require patience, measured in centuries or millennia. Even radio signals traveling at light speed would take generations to exchange simple messages. This isolation helps explain the famous Fermi paradox. If intelligent life is common in the galaxy, where is everybody? The question has haunted SETI researchers since Enrico Fermi first posed it over lunch in 1950. Various answers have been proposed. Perhaps civilizations destroy themselves before achieving interstellar capability. Perhaps they choose isolation deliberately. Perhaps something about the galaxy is fundamentally hostile to technological development. The Webb-informed answer suggests that everybody may be out there, but separated by distances that prevent meaningful contact. Each inhabited world exists in a bubble of isolation, defined by the loneliness radius. Communication attempts disperse into the vastness of interstellar space without finding receptive audiences within practical timescales. Consider a civilization 100 light-years from Earth that achieves radio technology and begins broadcasting. Their signals reach Earth 100 years after transmission. If we respond immediately, our reply reaches them 100 years later. The round-trip communication time spans 2 centuries. Neither civilization would maintain consistent attention to a conversation proceeding at such glacial pace. Now multiply this scenario across the galaxy. Thousands of civilizations might exist, each broadcasting hopefully into the void, each listening for responses that arrive centuries after transmission, each eventually concluding that the effort yields no practical return. The galaxy could be full of intelligent life that never meaningfully connects because the loneliness radius isolates each species within its own temporal bubble. This brings us back to the real problem that Webb's observations force us to confront. The local habitability illusion collapse is not merely a scientific curiosity affecting abstract questions about distant worlds. It restructures humanity's practical relationship with the cosmos. For decades, space advocacy assumed that nearby stars offered destinations. The vision of interstellar expansion imagined humanity spreading from world to world across the galaxy, establishing colonies on planets orbiting nearby stars, building a civilization that spanned light years. This vision motivated research funding, captured public imagination, and shaped scientific careers. Webb reveals that the nearby stars are not destinations, they are dead ends. Their planets cannot support human presence, or indeed any presence resembling Earth-based life. The expansion that seemed to await just beyond our technological reach actually awaits at distances that may forever exceed human capability. The psychological implications of this expanded loneliness radius deserve contemplation. Humanity grew up believing that cosmic neighbors might exist just beyond our technological reach. The stars seemed close when 4 light-years represented the primary barrier. We could imagine overcoming that distance within a century or two of focused development. Now we must imagine crossing distances that strain not just our technology, but our capacity for sustained purpose. A mission to a star 100 light-years away requires commitment from a civilization, not just a generation. The humans who launch such a mission would be launching it for descendants they will never meet. The connection between action and consequence stretches beyond any individual human experience. This temporal disconnection changes the character of interstellar ambition. Proxima Centauri missions could be motivated by individual human curiosity. The scientists who designed the probes could hope to analyze the data those probes returned. The connection between effort and reward remained within human experience, even if stretched across decades. Missions to the expanded loneliness radius break this connection entirely. They become acts of civilizational faith rather than individual exploration. They require humanity to function as a coherent entity across timescales that exceed any historical example of sustained collective purpose. The cathedral builders of medieval Europe offer partial analogy. Workers who laid foundation stones knew they would never see completed spires. Yet the timescales involved spanned generations, not centuries. The builders' grandchildren might attend services beneath finished vaults. The connection between labor and result remained within extended family experience. Interstellar missions to the loneliness radius would span timescales that dwarf cathedral construction. The connection between launch and arrival would stretch beyond any conceivable human relationship. We would be building cathedrals that our descendants' might one day enter. The motivation for such effort remains unclear, given human psychological architecture. Yet Webb's observations also provide clarity that has value in itself. The local habitability illusion encouraged planning based on false premises. Resources and attention focused on nearby systems that prove uninhabitable were ultimately resources misallocated. Better to know the true situation and plan accordingly than to discover the truth after committing to doomed destinations. The model strain that Webb observations reveal extends beyond habitability calculations. Our understanding of planetary formation, atmospheric evolution, and stellar environment effects all require revision. The models that predicted atmospheric retention on red dwarf planets underestimated the violence of these stars and overestimated the resilience of planetary atmospheres. This model strain is not a failure of science, but a success of observation. Models are tools for prediction based on available information. When new observations contradict predictions, the models must evolve. Webb is providing the observations that force this evolution. Future models will incorporate the hard lessons that current data teaches. The formation surprises extend to our understanding of how water and other volatiles distribute themselves during planetary assembly. Worlds in red dwarf systems may form with fundamentally different compositions than comparable worlds around sun-like stars. The radiation environment during formation affects chemistry in ways that previous models did not fully capture. These insights have value beyond the immediate question of nearby habitability. They improve our understanding of planetary science in ways that will benefit future observations. The search for habitable worlds does not end with the collapse of the local habitability illusion. It continues with better tools and refined understanding. Somewhere in the galaxy, genuinely habitable worlds exist. Webb's observations do not contradict this broader claim. The Milky Way contains hundreds of billions of stars. Even if habitability proves rare, rarity across such enormous numbers still yields significant absolute quantities. Millions of habitable worlds might exist throughout our galaxy, but they are not nearby, they are not accessible. They exist at distances that mock human ambition and humble technological capability. The search continues, but with adjusted expectations that fundamentally alter humanity's cosmic prospects. The philosophical weight of this cosmic isolation deserves acknowledgement without flinching. Humanity emerged on one small planet, orbiting one ordinary star. For millennia, We believed ourselves central to cosmic purpose. The Earth occupied the center of creation in ancient cosmologies. Humans held special status among living things. The universe existed for our benefit and instruction. The scientific revolution displaced Earth from the center of the universe. Copernicus showed that we orbit the Sun rather than the reverse. Galileo confirmed the evidence through telescopic observation. Kepler and Newton revealed the mathematical laws governing cosmic motions. Earth became one planet among several, orbiting one star among many. But this displacement came with compensation. If Earth was not central, perhaps we had company. Perhaps other worlds orbited other stars. Perhaps other beings gazed upon different constellations and wondered about their cosmic neighbours. The centrality we lost in position we might regain in connection. Webb's observations suggest that this compensating hope may also prove illusory. We are not central. We are not connected. We float in isolation more profound than previous generations imagined. The cosmic loneliness that seemed temporary, awaiting only technological development to overcome, may be permanent. The universe may simply be too large and too hostile for meaningful contact between its scattered inhabitants. This isolation carries a certain terrible grandeur. We are rare. Our planet, with its protective atmosphere and liquid water oceans and complex biosphere, represents an unusual combination of circumstances. The habitability we take for granted is not casually distributed across nearby star systems. It required specific conditions that many worlds do not possess. Earth orbits at precisely the right distance from a star of precisely the right type. Our moon stabilizes axial tilt, preventing climate oscillations that might sterilize the surface. Our Jupiter deflects comets that might otherwise bombard the inner solar system. Each factor contributes to habitability. Each factor could easily have been absent. The red dwarf planets Webb observes lack many of these protective features. They orbit too close to stars, too violent. They lack the magnetic fields necessary to preserve atmospheres. They formed in radiation environments that depleted volatile elements before planets could assemble. Each factor reflects the specific circumstances of planetary formation and evolution. Earth appears to have gotten lucky in ways that nearby exoplanets did not. Our habitability is not typical, it is exceptional. The conditions that allow life to flourish here cannot be expected to appear wherever rocky planets orbit in stellar habitable zones. The term habitable zone itself may require redefinition to acknowledge the many additional factors that habitability requires. The local habitability illusion has collapsed completely. Webb's observations leave no room for doubt on this point. The nearest promising star systems are not promising after all. Their planets orbit in radiation environments that strip atmospheres and sterilize surfaces. The chemistry Webb detects indicates conditions incompatible with life. As we understand it, our nearby future is worse than we believed. The cosmos is not merely indifferent to life, but actively hostile across most of the territory we had hoped might shelter it. Red dwarf stars that dominate our stellar neighborhood are not gentle hosts but violent destroyers. Their planets suffer continuous assault that eliminates the atmospheric protection necessary for habitability. This is not the message anyone wanted Webb to deliver. The telescope was built partly to search for habitable worlds and potential biosignatures. Its discoveries about the hostile nature of nearby systems represent a profound disappointment of those hopes. Scientists who dedicated careers to exoplanet characterization hoped to find evidence of water, perhaps even hints of biological activity. Instead, they find ambiguous signals and airless rock, but truth has value even when it disappoints. We now know that our immediate cosmic neighborhood cannot support the interstellar expansion that optimistic narratives anticipated. This knowledge protects against wasted effort and misplaced hope. It redirects attention toward more promising targets at greater distances, even if those distances exceed current technological reach. The knowledge also reframes humanity's relationship with Earth itself. If nearby alternatives do not exist, then this planet becomes not merely our current home, but potentially our only home for the foreseeable future of our species. The option of escape, of starting fresh on some new world when we have exhausted or ruined this one, recedes into fantasy. This reframing carries implications for environmental and social policy that extend far beyond astronomical curiosity. If we break Earth's habitability through climate change, nuclear war, or ecological collapse, we cannot simply relocate to Proxima Centauri b. That world cannot shelter us. No nearby world can. The loneliness radius therefore intersects with questions of civilizational survival in ways that astronomical observation rarely does. The findings from Webb Telescope carry weight for policy discussions that seem entirely unrelated to exoplanet characterization. The cosmic context of Earth's uniqueness informs how we should value and protect our only known habitable world. Yet even this practical implication rests upon the deeper philosophical recognition that Webb's observations demand. We face a universe that did not make habitability easy or common. The conditions for life require specific alignments of factors that could easily have been otherwise. Most planetary systems do not achieve these alignments. Most worlds are hostile. Most of the cosmos is empty of anything we would recognize as habitable. This recognition need not produce despair. The same observations that reveal cosmic hostility also reveal Earth's preciousness. We exist. Life flourishes here. Consciousness emerged against odds that now appear longer than we previously imagined. The very rarity that isolates us also elevates us. We are not common. We are exceptional. We represent something unusual in a universe dominated by barren rock and stellar violence. Webb will continue observing. It continues with better information and adjusted expectations. Perhaps somewhere dozens or hundreds of light years away, a world orbits in conditions that permit liquid water and atmospheric retention. Perhaps such worlds are more common around sun-like stars than around red dwarfs. Perhaps the loneliness radius, while larger than we hoped, does not extend infinitely, but the fundamental insight remains unchanged by future discoveries. The universe guards its habitable real estate behind barriers of distance and stellar violence. The nearby cosmos that seemed so rich with possibility has proven hostile and empty. Whatever cosmic neighbours we might have exist far beyond the horizon that earlier models drew, we are alone for all practical purposes. Not alone in the ultimate sense of being the only minds in the universe, but alone in the immediate sense that matters for human futures. No nearby harbour awaits our ships. No neighbouring civilization will answer our calls within timescales that individual humans can experience. The cosmic ocean we hope to sail proves more vast and more empty than our charts suggested. This loneliness defines our cosmic situation. Webb has measured it. The data leaves no room for the comfortable illusions that preceded it. We face the universe as it is, not as we hoped it would be. The stars that seemed so close when night fell on human cities were always more distant than they appeared. The refuge we sought among them does not exist within distances we can meaningfully traverse, and in that facing, perhaps we find a new appreciation for what we have. This pale blue dot with its thin atmosphere and fragile biosphere is not merely one habitable world among countless neighbours. It is a rare exception in a cosmos dominated by radiation-blasted wastelands and atmosphereless rocks. It is precious, beyond calculation. It is ours in a way that no other world can be for the foreseeable future of human existence. The local habitability illusion has collapsed. What remains is a universe vast and largely empty, with habitable worlds scattered across distances that humble human ambition. Webb has shown us the truth. The stars are farther than they seemed. The loneliness is deeper than we imagined. The isolation is more complete than we hoped. But we are here. We exist. We have achieved the remarkable feat of looking outward and understanding our situation. That understanding, however sobering, represents its own kind of triumph. We know where we stand. We know what we face. We know that the cosmos offers no easy alternatives to the planet we already inhabit. This knowledge must now inform how we proceed. Not toward nearby stars that cannot shelter us. Not toward destinations that exist only in outdated models, but toward deeper understanding of distant systems that might one day prove reachable, and toward renewed commitment to the one habitable world we actually possess. The loneliness radius defines the boundary of human aspiration for centuries to come. Within that boundary lies Earth, alone and precious. Beyond it lies the universe, vast and hostile, guarding whatever habitable worlds it contains behind barriers we cannot currently breach. Webb has measured this boundary. The measurement disappoints our hopes while clarifying our situation. We proceed from here with eyes open and illusions dispelled. The nearby future is worse than we believed. The cosmos is lonelier than we imagined, but we face these truths knowing that truth, however uncomfortable, serves better than comfortable illusion. The local habitability illusion has collapsed. In its place stands a clearer understanding of cosmic reality. That understanding will guide future exploration, future policy, and future philosophy. The stars are farther. The journey is longer. The isolation is deeper. But we know now. Webb has told us, and knowledge, even knowledge that disappoints, lights the path forward better than ignorance ever could.